So the next lecture we'll talk about X-ray diffraction. I would say probably X-ray diffraction is, I would almost say, almost the most useful technique. I mean, well, calorimetry, if I had to have one instrument in my laboratory, I would first of all have a calorimeter, but then I think I would have X-ray diffraction. And these slides and the chapter in the book are written by Ruben Snellings. He was working with me as a postdoc, but now he is in Belgium. He's working for this organization VITO, which is a state laboratory working on, well, lots of different things, but amongst them cementitious materials. So the outline of this presentation will be first to explain why X-ray diffraction is so useful, then some practical guidelines, particularly about specimen preparation, like I was asking before the break, and data analysis, and then some examples of application. So what can we do with X-ray diffraction? Well, I mean, it's really very, very useful because it can really tell you information about the different phases, but really they have to be crystalline. Okay, if we have one or two amorphous phases, we can determine their amounts by difference, and at the end I'll say a little bit about this technique, which is called PONCs, which can be used to quantify kind of not crystalline materials, but generally X-ray diffraction works on crystalline materials. And this can be used mainly for studying what's happening in hydration. You can also use it to understand your anhydrous materials, what is happening during grinding, etc. And the big advantage is it's a very quick technique now. If you have a modern diffractometer, you can take a very good quality X-ray pattern in about 15 minutes, half an hour. And with this very fast measurement technique, you can get an awful lot of information. I should point out there was really this revolution in X-ray detector systems happening about 20 years ago now. If you have an equipment that's more than 20 years old, then to get a good X-ray pattern would typically be 2 hours or more. And then the time was dramatically cut because they detect a part of the spectrum altogether. So just a brief historic perspective, X-rays were discovered in 1895 by Röntgen. And then already in 1912, there was started work on crystals with Van Laue, the Braggs in Cambridge. The first studies of cement were already in 1928 by Hansen and Brown-Miller. And of course, you may notice this name Brown-Miller is what gives its name to the ferrite phase in Portland cement, which is also called Brown-Millerite. And then back already in 1969, Rietveld put forward his Rietveld method for neutron diffraction. So all the mathematics was already established then, but the problem was that without modern computers, it was almost impossible to make the calculations you need to make for Rietveld analysis. So it wasn't really till much later, with a very gradual development, as you see here, over the next 20 and 30 years, that you really see the Rietveld method starting to be applied for quantitative phase analysis on cement. And since 2000, this has really taken off. Rietveld method has become a routine technique. More and more cement factories now have X-ray diffractometers. They can quantify the phase composition online. You have these automatic robots that take a clinker sample, grind it, put it in the X-ray diffraction, and give you the answer in in under half an hour. So it's really taken off, and also can be used for studying hydration. So this is a revolution. I mean, really, it makes completely redundant things like the Bogue calculation. Before we had Rietveld analysis, We would estimate the amounts of C3S, C3A, etc. by this bow calculation, but the bow calculation is very, very inaccurate. You may have differences of 10 or 20% even between the real phase content and the amount by the bow calculation. So I just can't underestimate the importance of Rietveld analysis in cement chemistry. So and why has it been a revolution? Because conventional X-ray diffraction, you're really up against this problem of peak overlap. So here are just some phases. I mean, here's the yellow, here's a CSA cement, here's a calcium aluminate cement, here's a Portland cement, here's a white Portland cement. And look, you know, all these phases, they all come in exactly the same place. It's not surprising because, you know, we basically have calcium, aluminium, and silicon oxides. So all the bond lengths, calcium to oxygen, silicon to oxygen, aluminium to oxygen, are all the same in these phases. And this is why they all have crystal structures with similar spacing. And you're not going to be able to get away from it. But the conventional methods where you would measure a single peak, I mean, quite honestly, forget about it because there's just so much overlap. They're really impossible to apply successfully. So now we're going to look at the basics, look at some of the common pitfalls, and talk about best practice. So the kind of apparatus that's classically used today is a diffractometer. I mean, this diffractometer technique has completely taken over from older tech. You had a lot of older techniques which use photography and things like that. But now, I mean, you hardly find those techniques anymore. It's all the diffractometer. And here you have a sample. Here's your sample. Here you have your X-ray source. And then at a certain angle, you will detect the X-rays. You have a detector. And then usually, I mean, there's different configurations, but usually you have a configuration where the X-ray source and the detector are moving in parallel and the sample is staying still. Okay? That's the usual configuration. You can get other configurations. And of course, if you're interested in single crystals, then you have completely different setups, but I'm not going to talk about those there now. So the measurement principle is you have a powder, you have lots of different crystals in many different orientations, and that's important because if you have lots of different orientation, you increase your chances of getting an X-ray reflection. Because if you just have a single crystal, you've got, you know, just points where you can get the X-ray diffraction. So you may not see it. So you have this powder, and then you, by spinning the sample, this sample is usually spinning, you compress the data into one dimension, and you get this pattern like this with the different peaks. And everybody makes this mistake, including myself. This is an X-ray diffractogram or an X-ray pattern. It's not a spectrum. A spectrum means you have a change in wavelength along here, and this is a change in angle, so it's not a spectrum. Everybody says it, but it's wrong. So practical guidelines for X-ray experiments. So what we want, as I said, we want to have a high number of particles to get the statistics of the diffraction. And we do that generally by grinding, reducing the particle size. And you really want particle sizes less than 10 to 20 microns, ideally 1 to 5 microns. And Ruben made a very nice study in our lab, and this is published, which shows that often when people are quantifying anhydrous cement, they will say there's amorphous content. But this amorphous content is purely because they haven't ground the sample well enough. If you ground the sample well enough, you will see that nearly all the anhydrous cement is crystalline. The amorphous content is below 1% or so. Although you can have an opposite problem that if you grind dry without lubrication, you may create amorphous phases on the other hand. So it's preferable to use wet grinding, which of course you can use for anhydrous materials if you do it in a solvent rather than water, but it can be a problem otherwise. And then you have the sample spinning. And this just shows the results from this study. This shows that as this is the unknown or amorphous content. If you have quite a coarse particle size, you could say we had about 25% amorphous, but when you grind it down to this figure of about 5 microns or so, you see it disappears to near 0. Okay, the next issue is how you load your sample holder. So the typical kind of samples holder you have here will be like this kind of disk. And the most common way of loading it is what's called front loading. So you have your sample holder, you put your powder on, and then you smooth it off. Now the big problem of this is that this creates preferential orientation, which we were talking about. So if you smooth off your sample, you will have horrendous preferential orientation. So that is really to be avoided. You can minimize that by what's called backloading. So here you have a sample holder which has a hole right the way through. You put it on a flat surface and then you put in your powder from the back. So you basically don't have to smooth off the top surface, and that helps a lot. You can still get a problem. And for example, with calcite, calcite also has a big problem like that. And for calcite, we actually developed another method, which isn't shown here, which is you fill from the front, but rather than smoothing off, you just gradually flatten your sample by tapping with the edge of a spatula in different orientations like that. So you don't get a perfectly smooth sample, and that does decrease the resolution, but you avoid the preferential orientation. And finally, there's this possibility to use a slice. Now, the big advantage of using a slice is that the paste holds the grains in place, and so you minimize preferential orientation. So we cut the slice on this cutting machine, very lightly level the surface with a very coarse polishing, not fine polishing, but very coarse polishing, and directly measure the slice. And this just shows the comparison. This is for anhydrite, which is particularly susceptible to this preferential orientation. You can see that with the conventional front loading, you've got this huge peak. You probably will only have 1 or 2% anhydrous in this sample. With front pressing, you can minimize that. Backloading, it's much, much better. So you really have to look at that. And if you have a problem with preferential orientation, what I would advise is to try several different preparation techniques and see how much the peaks that are susceptible are really changing. Because then if they're all more or less the same, then you're okay. And if you have ones that are, if you have a technique which has the smallest one, this is probably the best one. So there's no perfect answer, but that's some advice. The next point, of course, is hydration stoppage, and we talked about that in the last lecture. And this is a very nice comparison where you can see what's compared. So we have these phases, monocarbonate and ettringite, which are very, very susceptible to drying. And we have here a fresh slice not polished, fresh slice polished, the powder, then isopropanol, and slice polished and isopropanol powder. Now you have to look across all the range, because if we look here at portlandite, so portlandite is not susceptible to drying, but it is susceptible to preferential orientation. You can see that portlandite is not well detected in the fresh slice not polished, but it's more or less the same in all the other cases. So we would kind of dismiss that situation for the reason that it doesn't detect the portlandite well. And then if we look at the other ones, you see that it's pretty much the same for the fresh slice results. So this is why we're going for this fresh slice polished, because this is fairly good for monocarbonate, ettringite, and hemicarbonate, and also the portlandite. The other problem, which of course I talked about last time, is carbonation. And this very nicely shows this problem of carbonation. Here you have a fresh slice, and here you have a slice just exposed 2 hours. It's really, you think it's a really short time, But already, you look at this huge peak that's developed for the calcium carbonate. And that's particularly because calcium carbonate forms with a strong preferential orientation right at the surface. So you've got like the worst case scenario, because X-ray diffraction is only really measuring the surface of the sample, and that's the bit that's carbonated. So you see this dramatic effect of just leaving your sample lying around before you measure it. You really have to protect samples from carbonation. You can have a desiccator and just put in one of these proprietary products that absorbs CO2, like Carbazorb is one name, and that will give you an environment, keep your slices in there, and then transport them to the X-ray diffraction in that condition. So summarizing this is looking at the different methods we can have and that we're using in the lab. So one method that's rather nice, that works for a certain time, is you can look at hydration in situ. You have this holder, you have a Kapton film on the top surface, so you put in your liquid paste, and then you can observe the hydration every 15 minutes. It's quite good, but again, you have to be careful, because you can favor the preferential formation of crystals on the Kapton film. This is another problem. So always, really, you should compare, say, at 1 day between your in situ mix and separately prepared mix. Then we have this technique with the slice. If we take the slice without drying, we can have very good peaks for the ettringite and the other illuminate phases. The big problem is the carbonation if the method takes too long. If we dry the slice, we can have preferential orientation as well, and we can have effect of the ettringite and AFM, even if we're drying with isopropanol. So then we come to the powder. Backloading recommended, but we may have artifacts linked to drying. So there's nothing perfect, but that kind of summarizes the different techniques, and that's discussed in much more detail in the book. So that just sort of summarizes what I've already said, that the advantages, disadvantages between dried powder, slices and powders. Using fresh samples, we limit the changes on the hydrates, but we will have the problems with carbonation, etc. With the dried samples, then you will really lose your reflections from the ettringite AFM. If you're not worried about those phases, then it's not too much of a problem. They just become part of what is measured as the amorphous content. And then reporting. I said at the beginning that when you're using any technique, you should report it properly, and probably X-ray diffraction is the most important technique to report your data properly. Just even basic things. People are so used today that we use copper K-alpha radiation. They usually don't even report it. But there are instruments that have other kind of wavelengths, and other kind of wavelengths can be very good for some purposes, like going to smaller angles, smaller crystalline distances, for example. But these are all the things that you should really report, and that, of course, is listed in the book. So now we're going to talk about data analysis and this famous Rietveld method. So this was first proposed in 1969 by Professor Rietveld, and the idea is quite simple from a mathematical point of view. You have your experimental pattern. You generate in the computer what the pattern should be from your different phases. You add them up in the different amounts. You do a trial, so much of this, so much of that, and then you iterate. The problem is there's lots of different things you can iterate, and any of you who have studied mathematics know that if you have 100 or more parameters you can iterate, you can fit anything to anything. And that's the problem of Rietveld analysis. You have to control this iteration process, and there are some things you can vary and some things you can't vary. So this is the expression for the calculated pattern, And this contains an awful lot of things, but basically those things break down into these different categories. As first and foremost, the crystal structure. This is what you look up in a database, so that's generally fairly fixed. The phase scale factors are what you're trying to get at. This is the amounts of the different phases. There's a lot of instrumental factors, so each instrument will have different factors. There's a lot of factors related to diffraction optics, and there's other sample characteristics like preferential orientation, like particle size, things like that. This is another way of looking at it. This is the same intensity equation. This part here is coming from the, well, I mean, all of this part here is coming from the crystal structure. This is, I think, the instrument parameters and so on and so forth. But what the practical guidelines, that's what we want to get through. So first of all, you have to identify what phases you've got. So this is often called fingerprint analysis. You've got, in any X-ray diffraction equipment, you've got a database of different phases, and you match them up to make sure you've accounted for all the peaks. Now, what's important here is that you use your knowledge of what can be there. So if you just apply it in an uncontrolled way, the software will tell you there's all kinds of wild and exotic phases in your sample. And particularly because, you know, I talked about peak overlap at the beginning, and I explained to you that peak overlap is coming from the fact that cement is made up of these most common oxides, calcium, silicon, aluminium. But nearly every other mineral in the world also contains those oxides. So they'll also have peaks in similar places. So if you let this do it in an uncontrolled way, it'll tell you you've got all kind of wild and crazy things. So use your sense of what you know can be there. And you know, this is where it says a database of trustworthy patterns includes the major clinker phases and polymorphs, the minor ones, so the alkali sulfates, etc., alkali oxides. Sulfate phases you may add, like gypsum and anhydrite. The common SEMs, so they're generally amorphous, but fly ash and slag may have some crystalline phases present. The hydrates and carbonate phases. So, as it said here, many phases are suggested by the software. Difficult to find plausible matches for minor phases. So, you know, use your common sense. And a lot of this is down to experience. So sometimes you may have a problem here. It may not be trivial to identify all your phases. You may need to back it up by going to microscopic observations, for example, looking at the bulk chemistry of the sample, knowing where the materials came from. And you can particularly use this this method of selective dissolution to enrich certain phases. So that's what's shown on the next slide. This is what's commonly used for anhydrous Portland cement. You have these two extraction techniques. So one's called potassium hydroxide sugar extraction, or it's usually called COSH for short. And the other's called SAM, which is salicylic acid and methanol extraction. And these two techniques, this one here, the SAM technique, generally dissolves the calcium silicates, so it makes it easier to observe what you've got in terms of the aluminate and ferrite phase. And the COSH extraction does the opposite. So the COSH extraction removes the aluminate ferrite phases and makes it easier to identify what's going on with the calcium silicate. So particularly the determination of the C3S can be very sensitive to the polymorph type, or the different kind of pattern you use, and to know which pattern to choose, it can be very useful to do this selective dissolution to have the silicate phases without so much confusion from the aluminate ferrite phases. And then at the bottom here, you know, this is really to stress that the whole thing is an iterative procedure that, you do your peak identification, are all the peaks covered, and then when you've got all the peaks covered, then you can go to the quantification. So always, this is a few tips. Start with good literature structure models, so don't go off on your own. Usually what people have published in the literature is likely to be reliable. Minimize the number of refined variables, and this is perhaps the most important thing, because as I said at the beginning, you've got literally hundreds of things can vary, and if you let them all go wherever, you'll end up with nonsense. The final refinement, you should really know what you varied, and in routine quantitative phase analysis, this is what we're doing. We're refining only the scale factors and the lattice parameters. The scale factors have to vary because that's what you're trying to find out. The scale factor is the relative amounts of all the different phases. So that always has to be allowed to vary. And even the lattice parameters, you should not let them vary any old how. It's usually pretty well known that you can have a variation within a very narrow range, and you should restrict that range. So this is all part of this kind of learning procedure for applying Rietveld analysis. You really have to learn what's sensible and what's not sensible. Now, the big manufacturers have spent an awful lot of time putting all this data into databases. So if you buy an off-the-shelf system from either of the big manufacturers, which are particularly Panalytical and Bruker, they will both be pretty good for cementitious materials, because now both these companies have been developing the machines for cementitious materials for 20 or more years in terms of Rietveld analysis. They've incorporated all this basic stuff into their software, so their basic software will do quite well. But if you want to go that extra step, then you really have to look what's happening yourself, and particularly if you're going to start looking at more unusual materials, which may have different phases in or something like that, then you have to look at that. And it's not only, you don't only want to look at the fit in terms of the parameter you may get out in terms of a number, which we're going to talk about in a minute, but it's really important to look visually, to say, because you may have only a tiny bit where it's gone wrong, but you can see that very easily visually, whereas in terms of an average fit across the whole pattern, it doesn't come out very clearly. So that's really summarized all that here. This is what you can vary. This is what you shouldn't vary. Crystallite size, yes, that can be used. So not just going back, I mean, you very rarely have lattice strain. That lattice strain is a parameter you would use, say, in metals. Metals which have been mechanically deformed will have lattice strain, but not in cementitious materials. And if you're reporting Rietveld analysis, again, going back to the importance of reporting, these are all the different things you should report. You should say what kind of software you used, either from commercial producers or from academic people, what were the references you used for the patterns, etc., etc. And then you have, how good is it? You need to monitor how your fit is progressing. Generally, as I said, it's an iterative procedure. So you make a first stab at it, and then it updates and updates. And you need to see how it's going. You need to compare the fits you get with different models, and you need to measure the data quality. So as I underlined before, visual inspection is always important. Never rely just on numbers. And then you've got these various different numbers. And also you should check that something crazy hasn't gone wrong in terms of your structure requirements. So for example, if you're trying to refine a structure and you suddenly get bond lengths and angles which are completely crazy, then that's not what you want. And that just shows you an example of some of the kind of fit parameters you can have. Now, when you're looking at hydration, you have another problem, which is particularly annoying, shall I say it like that. And that problem is, it's like you're talking about these phases, but you're always talking about percents. You're talking about percent with regard to what? So if you have just the anhydrous here, right, you're talking about the amounts of the different anhydrous phases, like A light, B light, etc., relative to 100 grams of cement. But once you put it in a paste, then at the beginning, the whole paste is not just the anhydrous cement, but it's also the water. And as the hydration goes on, you get more and more of that water incorporated into the hydrate. So now, if we're at this time here, the amount of sample we're analyzing is much bigger than this amount here, even though it contained the same amount of anhydrous material at the beginning. Okay, so you're talking about normalizing with respect to a different weight. And you can correct all this. It's very well described in the chapter. But you need to know how much water is bound in your hydrates. And the best way of doing that is to do a complementary thermogravimetric analysis. So it depends on having the instrumentation. And we've talked about you slice, you put in the X-ray diffractometer, then you have to immediately take that slice, grind it up, take it to the TG.
In a few hours.
Well, you can take it, yeah, exactly, ideally.
To be practical.
To be practical.
In a few hours.
To get the best quality measurement, that's what you have to do. But in reality, you can grind it up and store it in a non-carbonating atmosphere and wait a little bit of time to, you can probably should wash it with acetone would be the best thing, or isopropanol, and then you can store it for a day or so. Can you
stop the hydration before doing the X-ray?
Well, as I say, usually we think it's best not to stop the hydration. If you have to, then do it with isopropanol, but except your acetone, yeah. But then when you have to grind it and put it for TG, then you have a bit more sort of possibility. But it's not ideal. And then you have to make this calculation. So you can calculate back, and you can either calculate on the basis of the dried weight, that's to say the amount of anhydrous you put in on the beginning, or you can calculate on the mass of total paste. But of course you have to say which one you're doing. Yeah.
It's not good for comparison.
Yeah. That just explains a little bit in more detail the kind of recalculation procedure you make, but I would really advise you to go and read that in the book because it's all explained in great detail there. And if you do it all properly, what's good is that you can really get then very, very close agreement. So this is for the thing that's probably easiest to measure. So the thing that's probably easiest to measure is the amount of C3S, the degree of reaction, because there's most of it there at the beginning. It's nicely crystallized, and it's not affected by drying. And when we do it all properly, you see we get very, very good agreement between the two methods. So going on with the examples, first of all showing the refinement. So this is a spectra you might have from, which is just a very simple mixture of rutile, which generally is always there because it's the most commonly used material for internal standard. So if you're measuring anhydrous materials and you want to have any determination of amorphous amount, you add generally 10% or so of rutile and the alite. So here we see that first of all we have to fit a background, and that's already refining two coefficients, and you see that that's your fit, not very good. Then you introduce the rutile, and your fit parameter actually goes down. I'm not sure. And there you see we've got very nicely the rutile peaks, and we want this to go as low as possible. And now we're putting in the alite, and you see it's improved. And now we're adjusting slightly the lattice parameters of the A-light and the rutile, so that we get this fit parameter is going down even lower, and so on and so on. So these are all the different things that you can do, and you can end up with typically a fit parameter of about 7%, which is meant to be pretty good. And this tells you, if you look here in these last few, you can see how much difference it's making. So this very first one here, we came up with 25% rutile and 74% triclinic. And that was probably pretty good, because almost certainly in this case, we introduced 25% rutile. And here you see it's 2673, here it's 2673, 27. So, you know, it's changing around, but it's not necessarily changing towards what you want. You know, this is the problem, you know, because here they've introduced all these other parameters like preferred orientation when you don't generally have much preferred orientation of A-light. So you shouldn't have been refining that. And it little bit shows you the pitfalls you can get into. But at the end of the day, it's really not too bad, because the kind of error we've got in the determination of these things is generally 2 or 3%. Okay? Now, if we go to a more difficult one, the phase composition of cements, we have, oh gosh, yes, this is another problem. We have now the problem that we have phases which have very different mass absorption coefficients. So the anhydrous phase is not too bad, because they're all kind of the similar atomic weights in terms of atoms. When we go to hydrates and we have a lot of water, we have also, should also scale for this mass absorption coefficient. And then we have to do this calibration using either an internal or external standard. Now, what's the difference between internal and external standard? Well, internal standard, if you read in the text, is usually promoted as the best method. And it is the best method in many senses, because what you do, if you do it in the way it should be done, that's to say, you take a powder, you powder it, you grind your sample, and then you mix it with the internal standard powder. But what you mustn't do is put your internal standard in before you do the hydration. Because if you put your internal standard in before you do the hydration, then it changes the hydration kinetics, and it changes the phases that form, and you have everything. And also, if you want to use fresh slices, then of course you don't have a good way, where have I gone? You don't have a good way of putting in an internal standard, because you've made your slice, and I've just said you can't put it in before you do the hydration. So what do? So then you go to this external standard addition. Now, external standard addition, it's like a virtual standard. So what you do, you have your sample, you do the X-ray pattern for the sample, then you do the X-ray pattern for the standard. And you have to measure the standard and the pattern really at pretty much the same time. Okay, so if you've got, say, 10 samples, you can measure 10 samples and then straight away after the standard, because then you've got a time difference of just a few hours. That's okay. But don't measure your standard on Monday and then assume that's going to be good for the whole of the week, because it's not. Because any X-ray equipment, the tube gradually goes down and down and down with time. So you have to, you can use external standard method, it works very well, but you have to measure external standard regularly in the same series of measurements where you've got your experimental samples, you know, every 10, 20 samples or so. And here we can see the kind of complexity we have. Here we see all the different phases that have come out of this Rietveld analysis. You've got the anhydrous phases here and the hydrated phases. And altogether, this does work really, really well. And there was a nice paper we published just earlier this year where we could really show for very complex systems containing slag and fly ash and limestone how you could really well match up the phase assemblages by using mainly X-ray diffraction, but then complemented by SEM analysis, particularly to get the composition of the CSH, and putting it all into a mass balance framework. So you can get very accurate phase assemblies, but you really need to follow it through, and that's well described in that paper where I can give the reference afterwards. So this is another example where you may want to use that in production process. So this is a production process in a factory where they're looking at A light and B light, and particularly free lime, because of course free lime is a very important indicator when you haven't had proper clinkering taking place. And you can see as the free lime's going up, then the A light content is going down and the B light content is going up. And clearly that's a very important thing to be aware of. And that's why, as I say, many factories now have online Rietveld analysis. You can also use it to look at kinetics. So this is the kinetics of a hydrating zeolite cement. This is where all the patterns have been stacked up. And this is quite nice because you can see the time here. You can see, for example, calcium hydroxide building up here and here and here. You can see your CSH, even your, this is a broad amorphous hump, but you can still see something of your CSH and all your other hydrates, etc. And here we're looking, this is then analysis of that data, so that's a kind of visual representation of things hydrating. What's usually much more useful is to have this kind of depiction, because this is then quantitative. All these patterns have been through a separate Rietveld analysis, and we can really follow, how so this is the C3S, which is hydrating here. This is in minutes. And then these are the hydrates forming here. So we see particularly the calcium hydroxide, and then we can see the other hydrate phases and the other anhydrous. Now, of course, what we really want to have is to look at the amorphous content. Is often we want to detect amorphous content. So this can be important for SCMs, which have a lot of amorphous content, like slag and fly ash. This can be important, of course, for detecting calcium silicate hydrate, which is the main hydrate important in cement. And we may have other situations where we want to know amounts of amorphous content. And as I said, the classic approach is to use an internal standard, either an internal standard or an external standard. And these both work very well, but the problem is they both give you the total missing content. So they give, if you have like a slag hydrating, it gives you the total of the unreacted slag plus the CSH. And that's not so convenient because you really want to know independently what the other methods are. So we've started using this PONCS method. So this stands for pattern of no known crystal structure, which is why it's written with K before the C, which you wouldn't normally do. Okay, so pattern of no known crystal structure is what it stands for. And this basically fits a pattern, not with peaks, which you calculate, but with humps. And it's quite nice because you can take a crystalline pattern, like, for example, you can take tobermorite, and you can kind of degrade it a bit, so it becomes your CSH structure, and it works quite well. And this is all the mathematics behind it. I'm not going to go through that in detail. You can read that in the book, but this is more visually how it works. That here we've got a pattern which is an OPC with slag, and we want to determine the slag. So you make this pattern at the top is just the slag, and you see you fit this kind of hump here with the slag. And here, it works well because this is an anhydrous sample where we just have the slag and the Portland cement. And we can get back the amount of slag very, very well. So this is just one amorphous phase. Works quite well. But if you then hydrated this mixture, you have a big problem because basically CSH is in exactly the same place and it doesn't work so well. On the other hand, if you have something like metakaolin, which has a hump in quite a different place, it works better, but still not perfectly. this is what's shown. So this is now the example with metakaolin. So this is hydrated cement with metakaolin. This is quite nice because now we've got this is the peak for the CSH here. No, sorry, this is the peak for the metakaolin. And this is the one from the CSH here. So you can see they're nicely separated. But if I go back to that slag one at 30 is now in exactly the same position as that CSH one. So that doesn't work so well. So it's not bad, this Ponck's technique, but it's pretty limited in terms of what things you can apply it to. And as discussed in this paper, which I referred to earlier, really, if you have complex mixtures, it's better to use complementary techniques. Like with slag, the best technique is the image analysis to look at degree of hydration. With metakaolin, the best technique is using a kind of fitting to the calcium hydroxide. Somebody was asking you about calcium hydroxide, and basically there is a method you can use, but it's quite complicated. So conclusions on this part, I think you really X-ray diffraction is a very, very important tool. You can characterize all these different phases, straightforward, relatively straightforward sample preparation. I've talked about all the problems with preferred orientation, but these are as nothing compared to SEM. SEM, where you have to polish samples, is 10 times more difficult. Short measurement times, it's accessible in most labs. That's a major point. Practically many people have. And we can do this automatic analysis in cement production. What are your limitations? Well, you're never going to get accurate than about 1 to 2% absolute for major phases. Sorry, 2 to 3 for major phases, 1 to 2 for minor phases. And you do need a certain amount of expertise if you're not going to do routine analysis. If you're going to do absolute routine things, then the off-the-shelf software from the major producers will do a pretty good job. But the moment you get into a research situation where you've got slightly different materials, then you really need to have expert knowledge. And those are some of the references. There's a lot more in the book.